everyone, welcome back to another video of Daily LeetCode Challenge Streak Series, and in today's video we have a new question that says Pseudo Palindromic Paths in a binary tree. Now let's read the question. Given a binary tree where node values are digits from 1 to 9, a path in the binary tree is said to be pseudo palindromic if at least one permutation of the node values in the path is a palindrome. Return the number of pseudo palindromic paths going from root node to the leaf nodes. Now, what does the question say? If you start from the root and traverse through all the nodes, and in one particular path, you have to check for all the combinations within the given elements of a particular path and see, even if you rearrange the given elements, whether or not they form a palindromic. For example, one such path is, let me take a different color. One such path is 2, 3 and 3. So if you take this part 2, 3, 3, if you rearrange it, this becomes 3, 2, 3. Now, if you carefully observe, this number is a palindrome. So, whatever the path is, it's not necessary that the path that you have taken should be a palindrome. You can rearrange it, as in if you take any permutation, as in if you rearrange the values of it and whatever value you get, if it is a palindrome, then that is one palindromic path. Now, you have to check for the number of such palindromic paths from the root node to the leaf nodes. Now, very simple. Now, what is the condition for a number to be a palindrome? What is the condition? Now, we have two types of palindromes. One, the odd number of palindromes. One with the even number. Let's consider an odd number of palindrome. For example, 1, 2 and 1. If you carefully observe 1, 2 and 1, I have 1 and 1 cancel, and the only number that I have left is an odd number that occurs only one time. Okay? A number that is left after balancing of the other numbers, I have only one number, which is odd number of occurrences. Now, 2. If you take an even number like 2, 3, 3 and 2, you can see that you can balance off all the numbers. Like there is no number that occurs for odd number of times. If it occurs for even number of times, you can balance the numbers off. You can balance the numbers off in the middle. Now, what do you have to check? You have to check that any number within the path to see that if there should at most be only one element, okay, there should only be one element with odd number of occurrences. Only one element. There can be 0 occurrences also with odd numbers, it doesn't matter. But if there is any element with the odd number of occurrences, it should be only one element, that too its frequency should only be 1. Its element should only be 1. Because if it is 3, it will be like 2 plus 1 and 2 gets cancelled off and it will still be 1. At most only one element can have odd occurrence. Why? Because if it's 1, 2, 3 and 1 and 1, 1 gets cancelled out. Now 2 has odd number of occurrences as well as 3 has odd number of occurrences. So, is this a palindrome? No, it is not. Instead, if I had 1, 2, 2 and 1, 1 and 1 have even number of occurrences, which is 2. Likewise, 2 also has even number of occurrences. So, cancel off. So, is this a palindrome? Yes, it is a palindrome. Now, very simple. How can we solve this question? Now, what we can do is that we can take this path. Okay, let me just write it down here again. 2, 3, 3, 1, 1, 1. Now, what we can do is that we can start from the root node and we can traverse down till all the paths. Now, the minute we reach a leaf node is nothing but which doesn't have a left and a right node, which is in the last level of a tree. Now, once we reach the leaf node, we will take all the elements from that path and we are going to check how many elements have odd number of occurrences. If more than one element, like in this example, have odd number of occurrences, like here if you see 2 and 3 both have one number of occurrences. So this can't be a palindrome. So if any number has more than one number of odd occurrences, then you will immediately return false. It means that this is not a palindromic path. Now, what you will do next? If for only one element, if the occurrence in this whole path of elements, if the occurrence is less than or equal to 1, if it is, less than or equal to 1, it means that it is a palindrome. It means that the number of occurrences of odd number is either just 1 or 0, as in it doesn't have any odd numbers. In that case, it is a palindrome. So you will simply return a true. Now next, what will you do after returning true or false? You will backtrack to the previous element. You will just backtrack to the previous element and you will explore a different path, correct? Now initially you started at 2, went to 3 and then you went to 3 again. Now next, once you backtrack, since you have gotten your answer here, you will just backtrack here and then check with this path. And then after getting your answer, you will again backtrack and you will come here. So what are you doing? You can first go to root, then left, then it's left. Then you will go back, then it's right again. So root, left and right, root, left and right. So which order is this? Which kind of traversal is this? This is in-order traversal. So you will just apply in-order traversal on the tree. Let me write it down. You will apply in-order traversal and after reaching the leaf node, you will check for the palindromic path. You will check whether or not the given path is palindromic and you will verify this another helper function. You will verify this using another helper function. Now after you get the result, what you will do? You will backtrack, okay? You will backtrack. Now in case you will backtrack and while backtracking you will count. Now also while traversing from the root node, you are going to count all the occurrences of every element. If you are at 2 and then 3 and at 3 again, you are going to take this 2 and update its frequency to 1 in a frequency map. Then go to 2 whenever you encounter 3. From 0 it becomes 1. Then when you get 3 again, you will update this to 2. So 3 becomes 2. Now, after you finish the leaf node, you will check for odd number of occurrences for only one element. Once you return, you are backtracking. Now, while backtracking, what you are going to do? You will decrement its count by 1. Okay, you will decrement its count by 1. So, 2 is still 1 and 3 becomes 1 now because you have decremented it. You can only find whether or not it's palindrome or not by having the occurrences count. Now, what will happen? Then you will go to 1 here. When you go to 1 here, the 1 count becomes 1. Now, you can see that all the elements here have an occurrence of 1 only. All the elements here have an occurrence of 1. It means that the number of elements having odd number of occurrences is greater than 1. So, this cannot be a palindrome. Now, you will again return a false and you will delete this count. When you go back, you will decrement this count. So, 1 becomes 0. So, the minute any value's occurrence becomes 0, the value becomes 0, you will be deleting the key element as well because you don't have to waste the space because there's if the element comes up again in the root, we will add that element and then we'll write the frequency. But if the element is not there, why do we have to waste the space? So it is not needed. So you will traverse, you will keep the count of every element and occurrences, and if the count becomes to 0 while decrementing, then you will delete that element from this dictionary or the frequency map that you are having. In the end, whatever counter is there, you will have a counter element separately that will increment the count whenever there is a true return from the palindromic function. So whenever a true is given from this, whenever you get a true, you will increment that result count. And once you finish traversing all the elements in this particular tree, you will return that result. Okay. Now the concept that we are applying here is depth first search. So for every element we are going and then we are backtracking back to the original path and maintaining the counts. What is the time complexity here? Since you are going through all the elements, since you are traversing all the elements, the time complexity would be O of n. Now, what is the space complexity? Now, when you are traversing, you are trying to keep the count of elements of one particular level. So, if you complete one path and when you are coming back, usually you tend to delete elements if that element is not present. If the count of that becomes 0, you tend to delete the space for that particular element. So, predominantly when you are traversing, you are only keeping a count for the height of elements in that particular path. So, if the height is 1, 2 and 3, the dictionary for now would only contain 3 elements or even 2 elements for that matter, since these are same here. Okay, so the space complexity would be O of the height of the tree. Okay, so let's quickly code this up. we have a function pseudo palindromic paths given in which a root is being sent, as in this tree's root, and we already have the definition for the binary tree here, which is defined for the value for the left and the right. Now what do we need for the solution? We need two functions, one function to check whether or not a given path is palindrome, and another function to traverse through the tree, a DFS function to traverse through the tree. And in the end, what are we returning? We are returning the DFS starting from this root and its number of palindromic paths. So root comma. Now I'm initializing this root and an empty path and sending it back to a function DFS which takes the node and the path, The path is the dictionary in which we are going to store the element and its frequency in the current path, Now also along with this, what do we have? We need a helper function to check if it is palindromic or not. Let's initialize that as well. Is palindrome. Now next, first let's fill this function up. DFS. In DFS, what we are doing, if there is no node, okay, if it is not a node and if it's an empty tree, then we will return 0. Okay, we are going to return 0. Next, what are we doing? If we come across any particular value in a tree, what are we doing? We are incrementing the node's value in this particular dictionary by 1. So path of node.val, it is val because here it is initialized as val. So path of node.val is equal to path.get node.val comma 0, and we are incrementing it. Now why did we write a 0 here? In case we come across a new element that we haven't come across before, its occurrence is first initialized to 0 and then we will be adding 1. If there is a count already, then we can directly add 1. If there is not a value in there, then we'll be initializing it to 0 first and then adding 1. Okay, this is the first condition. Now, then it will keep recursively going down. But what if we are at leaf node? What is the condition for the leaf node? It means that there is no left and there is no right. If not node.left and not node.right, then what are we doing? It means that we are at the end. If we are at the end, what are we checking? Now when we are at the end, we are checking if the element is palindrome or not. If the element is palindrome or not, and then what are we doing? We are adding it to our result. Okay, we are adding it to our result where we are keeping a count of the number of palindromic paths. Okay, the number of palindromic paths. It means that result equals to 1. If result equal to 1, it means that the palindrome is present. Okay, if result equals to 1, it means that if is palindrome of path, it means that the result, it is a palindrome. It is returning a palindrome. Okay, else we will not add anything. We will add 1 to the result if it is a palindrome, else not. Now before we continue any further, what do we write in the palindrome function? First, since we are only checking for the number of at most one element to have odd count to be 1. So let's initialize this odd count variable to 0 first, and then we will count the frequency of every element in this given path. So for count in path.values, if it is path.key, then we are talking about the element. If it's path.values, then we are talking about the frequency. Then what are we doing? If count mod 2 equals 1, it means that it is an odd number. If this is an odd number, we will increment the odd count by 1. Okay, if count mod 2 is equal to 1, okay, it means that it is an odd number. Then we are going to increment the value by 1. Okay, else, okay, there is no else condition because we are only checking for the odd number. Now what are we going to return? We will return a true if this odd count is less than or equal to 1. So return odd count less than or equal to 1. So it will automatically, like I told you in the previous videos, if you write it like this, it will automatically check for the condition and return a true or false according to the condition given. So if this condition here is true, it means that if odd count here is less than or equal to 1, a true will be returned, otherwise a false will be returned. Okay, now since we have finished our palindromic function, where are we? If the leaf node, if we are at leaf node and the path is done, we are checking for palindrome. So result will be 1. If the palindromic path is 2, it means that if it is less than or equal to 1, at most one element has only one odd occurrence. Otherwise, the result will be 0. Okay, else what if it's not the leaf node and what we are at some middle node or the starting node? Then we will traverse to left and right again, correct? If we are not at the leaf node, then again we will traverse to the tree further. So we will be calling our function. So dfs of node dot left comma path plus dfs of node dot right comma path. Okay, this is what is this? It is result. Okay, it is just the result. Since we are sending it into the result only, since we are directly returning the result in this only, we'll be storing this value here. Now what are we checking next? Our two conditions are over, if it's leaf node or if it's not leaf node. Now we have finished our path. Now we are going back. Now while backtracking, what are we checking? What happens while we are backtracking? The count decreases. Okay, the counter decreases, and after the count gets decreased, at any point if the counter of some value becomes 0, we are removing that value from the path because we don't need extra space. Okay, what are we doing? Path of node dot val is decremented by 1, if path of node dot val equals 0, it means that its value has become 0. Then we are going to delete that particular value. Okay, so node, we are going to delete that val. Now in the end, what are we doing? We are just returning the result, correct? We are returning this result after it gets added. Like, okay, in palindrome function we are sending path, and in the end here we are returning dfs of, like, since we are returning this one, so we will start with the root node and then an empty dictionary and return our answer. Now let's quickly run the code. This works, and let's just submit it. Alright, this works. Like we've discussed earlier, the time complexity is O of n and the space complexity is O of height of the binary tree.